So good afternoon, everyone. Welcome to this webinar. We are really, sorry, my name is Francesco Petruccione, but I think the people that are here present today probably know me all, but maybe some other people might watch it later. We are very lucky this afternoon to have Dr. Daniel Burgarth with us. Daniel and I go back a long time in a common era that we spent at the University of Freiburg in Germany. And from that time also is Daniel and I and Heinz-Peter Breuer wrote a paper that at that time we thought was just a simple exercise, but it turned out to be a very highly cited paper that influenced many further works. So thank you, Daniel, for that. Yeah. So Daniel, after his master's at the University of Freiburg, moved to London, to UCL, where he did his PhD with Sugato Bose. And Daniel, please correct me, I'm just talking out of memory. So I might get the facts not completely right. Yeah. And after that, he spent some time, was it in St. Andrews, Daniel, that you were?
I did a random walk. So I was in Zurich and then in Oxford, then in London again. Yeah. And then I went to Aberystwyth. That's probably what you meant in Wales.
Yes. Sorry. Yeah, okay, not too far away. Yeah, and since a couple of years, he moved to Sydney. Yeah, where that's probably, I don't know if one can say the end station, but probably it's a more permanent station. Yeah. So Daniel, thank you very much for agreeing to be with us this afternoon, and we are very much looking forward to your talk. So if you would like to start sharing the screen, you're most than welcome to start, because I know it's late for you, so we don't want to hold you too long. Yeah.
Thank you. Thank you so much for inviting me, Francesco. And indeed, we do go back a long time. I just looked it up, and I think we started working together 2003. Yeah. And it was really Francesco who opened the world for me in terms of non-Markovianity and open quantum systems. And I'm very happy to give a seminar here, which is kind of very close to that. So I've sometimes moved a little bit away from open quantum systems, but I'm always coming back to it. And the subject that I'm talking about today will be very much on open quantum systems, namely on some sort of GKS structures and its interplay with perturbation theory, you might say. I should also say that at the time, it didn't feel like a little exercise to me. I think this is the perspective of a master's student, that everything feels overwhelming and big. Yes, so thank you again. And I have to say that I've also visited Durban. I think it was maybe 2011 or something like that, or 2009 or so.
Something like that.
Also some time ago, but it was great to be there, and I wish I could be there right now as well, and join you guys for a coffee outside or something like that. We have winter now. When we are all
vaccinated, we will invite you again. Yeah.
Thank you. Yeah, and you have winter as well, right? But your winter is probably warmer than our winter. Anyway. Let me share my slides before I waffle too much. I forgot how to do that. Let me start.
There is a green button in the middle at the bottom.
Yes, I just realized I have to start the presentation first.
Yes,
right?
yes. And then the green button finds your PowerPoint or Keynote or whatever you're using. Yeah.
Okay, I think I'm almost getting there.
No problem.
There we go. Can you see that?
Yes, perfect. Thank you very much.
And can you see my mouse pointer as well?
Yes.
Excellent. Okay, so please feel free to interrupt me at any time if you have any questions. I consider this as an informal style seminar. I probably prefer questions during the talk to questions at the end. So the title of my talk is Eternal Adiabaticity and KAM-Stability. So some of you might be familiar with KAM-Stability as a concept from classical mechanics. So here it's in the framework of quantum mechanics that I want to talk about KAM-Stability, and hence there is a little spin here. And the focus of the talk, however, will be less on the KAM story, which requires some pre-knowledge on KAM, but it's more about this aspect of eternal adiabaticity. And I highlighted the word eternal because at the moment, I'm really keen on doing things that last a long time, and maybe that's a side effect of me aging. And this is a joint work with Paolo, Facchi, Hiromichi, Nakazato, Saverio, Pascazio, and Kazuya Yuasa. So it's a Japanese collaboration with Waseda University and an Italian collaboration with Bari University. And it was recently published in 2 papers, which are easy to find. Okay, hang on a second, something not working. Okay, let me give you an overview of the talk first. So I want to approach the subject less from a physical perspective, but more from a mathematical perspective. I want to give you a mathematical definition of eternal adiabaticity. And in doing so, I will make some ansatz for the definition, which will be either too simple, so it will be trivial, or it will be impossible to solve. And I will alternate between simple and impossible until I find something that is a good definition. But this motivation will be entirely from a mathematical perspective. And I think that's the easiest way to introduce this pedagogically, let's say. And then only then I will show that this is actually a useful property for quantum dynamics, in particular if you look at the stability of quantum dynamics. Stability as in stability to perturbations, for example. I then want to characterize which kind of systems enjoy this property, because it's a really useful property. And however, the focus of this talk will be on the physical structure of this eternal adiabaticity in the context of open quantum systems. And that brings me home to this question of what is a valid generator of an open system dynamics. And I will spend most of this talk, and I apologize to Francesco, who has already seen this talk in tone. I haven't changed much. I will spend most of it on presenting a counterexample, a really annoying counterexample, which took us a long time to find. But once we have it, it disproves something which we would have hoped wasn't. I mean, it disproves something nice. So we found it annoying. And I will also present this in annoying detail. So maybe for some of you, this will be interesting because some of the methods that we use, even if you're not interested in this particular counterexample itself, you might be interested in the methods we have used to find it, which is very much about validity of a generator in open systems and how to see whether such a generator is valid or not. Okay, but first let's start with this mathematic thing. So we develop an axiomatic approach, a definition, which will oscillate between too simple and too hard. So to start with, forget about all of quantum mechanics and just think of 2 matrices. If you insist thinking about quantum mechanics, maybe think of them as Hamiltonians, but I'm not imposing any particular structure. They can be arbitrary at the moment. And I ask whether there is a third matrix, C, given 2 matrices A, and B, such that C and A commute. Okay, this is already too trivial because, of course, you can always choose C, the 0 matrix. So I need a constraint. And the constraint is that I want the spectrum of the sum of A and B to be equal to the spectrum of the sum of A and C. And in this sense, one could think of C as some kind of approximation. Why? Because the spectrum, if you're interested in the spectrum, then if you replace B with C, the spectrum doesn't change. So you could say this is an approximation. However, it is at the moment not really an approximation, and hence I put quotation marks here, because I'm not actually asking that C has to be close to B. I'm just asking for the spectrum pretty the same, and for commutativity. Let me clarify this approach by an example. So here's the matrix A that I'm just choosing as simple as I can. So this is essentially Pauli Z with a scaling factor. And B is Pauli X with a scaling factor. And I'm asking, well, is there such a matrix C? Well, first of all, I have to compute the spectrum of A plus B. But this is easy because A plus B with the 2, 1 over square root of 2 is just essentially like a Pauli matrix in a different direction. So the spectrum is just -1 and 1. And so I have to find a matrix C which commutes with A. And when I add it to A, gives me the spectrum 1 and -1. Well, that's easy. I just choose C proportional to sigma Z as well. So then, of course, C and A commute. And you see, if you add A and C, essentially what you're doing is you're removing A and replacing this 1 over square root of 2 with 1. And of course, that has the correct spectrum. This is not the unique choice. I could have also instead have chosen this particular matrix C prime with a minus sign here. And again, it replaces it. It's just that the spectrum is the other way around. The order of the spectrum doesn't matter. I just ask it to be the same. Now this generalizes immediately to any pair of matrices that is diagonalizable. So if we look at a diagonal basis, we can write the matrix A with its eigenvalues. And then the spectrum of A plus B is an arbitrary set of numbers. Let's call them lambda 1 to lambda n. And so C, if C is diagonal in the same basis in which A is diagonal, it commutes with A. So that's the first condition we have. And then if we choose the diagonal values so that they remove the diagonal values of A and replace them with lambda, then it's immediately clear that the spectrum of A plus C is equal to the spectrum of A plus B. So this, I argue, is trivially possible. So you could say that this definition is too simple. But this is only the diagonalizable case. So what about non-diagonalizability? So here's a fun fact for, let's preview a little bit of quantum mechanics already at this point, although what I say now is mostly mathematical. But if you're more interested in open quantum systems, in Gorini, Kosakowski, Lindblad, Sudarshan generators, then this might be a fun fact for you, because we often assume in physics that everything is diagonalizable, but it's very easy to find examples of non-diagonalizable things. And such GKLS generators are good examples for that. So here is a particular GKLS generator which eats the density matrix and is given by a commutator with Pauli Z. And this term here, for those of you who have worked on open quantum systems, will be familiar as some sort of dephasing in the X direction. So this is a fairly common type of generator of Lindbladian dynamics. And I would like to argue that this generator is actually not diagonalizable. So in order to understand this, I'm going into a matrix representation. If this is unfamiliar to you, this is essentially moving from a super operator to a matrix on a higher dimensional space. I will explain that later. Let me just take this as a given, but you might, for example, recognize there's a sigma x here, and there's a sigma x here, and there's this I here goes on the diagonal. So this is a kind of matrix representation. And so obviously, if I want to discuss whether that matrix is diagonalizable, it suffices to look at the component that is not proportional to the identity. And you see here, there's a block inside. And so if I compute the spectrum of this block, I have to compute the characteristic polynomial of this block. And you see here, there's a minus I squared and a -1. This goes to 0. So we have lambda squared equal to 0. So this little block here in the matrix has eigenvalues 0 twice, twofold. But it is not the zero matrix. Well, if a matrix has eigenvalues zeros only and is diagonalizable, then it's clearly the zero matrix. But this little block is not the zero matrix. So therefore, this GKLS generator, which is very cute and simple, is not diagonalizable. And it's a sort of degeneracy that happens only for the value 2 here. If you put a 2.1 or something like that, it already becomes diagonalizable. But anyway, this is a good example of something that is non-diagonalizable. Okay, so we need to look at the non-diagonalizable case. This is why I gave you this example. And in the non-diagonalizable case, commutativity is a bit too strong. So let me explain this. So for example, this is another non-diagonalizable matrix. Now just forget about the physics again, it's just some 2 by 2 matrix. It has eigenvalues 0 and 0. It's tri-diagonal, so you can read off the eigenvalues on the diagonal, but it is not the it's not the zero matrix, so it's therefore non-diagonalizable. And let's ask which matrix C, which I keep arbitrary, commutes with A. This can be solved easily. You just compute the commutator of A and C. And this has to be 0. And this gives you some condition. For example, C3 must be 0. Also, C4 must be equal to C1. So C takes this particular structure here. This is an arbitrary matrix which commutes with A. But you see now, the spectrum of A plus C, when you add this matrix with that matrix, will always have a tridiagonal shape and will always have C1s on the diagonal. So the spectrum of A plus C, irrespectively of how we choose it, it will always be degenerate. On the other hand, we can choose a matrix B such that the spectrum of A plus B is not degenerate. For example, here's an example case. So the spectrum of A plus B is now 1 and 0, which is non-degenerate, and you cannot mimic this with any C that commutes with A. So generally, commutativity and spectral preservation are impossible for non-diagonalizable cases. Commuting is a too strong constraint for the non-diagonalizable case. So we need to weaken our definition a little bit to make it feasible again. So this is what I'm going to do now. So now I would like to consider again 2 matrices, but because I want to refine this commutativity into something else, I have to give you the spectral decomposition of the matrix A. Now, if A is diagonalizable, this would be just this first term here. But if A is non-diagonalizable, which is a case I don't want to exclude, I have these nilpotent parts here. And so some of you might be familiar with this in the context of the Jordan normal form. This is just an abstract way of writing down the Jordan normal form of a matrix. So this is always possible for any matrix A. Then I asked the question, is there a C? But now I'm not asking for it to commute with A, but I'm just asking for C to commute with the spectral projections of A. So essentially to have the same block structure. You see the nilpotents, they live in the same blocks as well, but they live on the off diagonal. What I'm asking is that C commutes with the spectral projections. This is weaker. And I'm still asking for it to mimic the spectrum of A plus B. So the spectrum of A plus B should be equal to the spectrum of A plus C. Again, let's look at an example to make this abstract definition a bit clearer. Here is a non-diagonalizable matrix. I already put it in the Jordan form. Maybe this will be more recognizable for you. We have a degenerate eigenvalue A1 here, and we have an off-diagonal block here, which is a Jordan block. We have a projection. We have 2 projections, one for each eigenvalue. The summation here only goes over distinct eigenvalues. And we have 1 nilpotent. The other nilpotent is just the 0 matrix, the one corresponding to this eigenvalue down here. The spectrum of A plus B can be arbitrary. Of course, B in general will lift the degeneracy. So sometimes A plus B might be actually diagonalizable, but we don't really care about this. And then we do the same trick that we did before. We need C to commute with the spectral projections. Well, that just means it needs to be diagonal in the Jordan basis of A. that's easy. And then we can just, again, do the same trick. We subtract the eigenvalues of A and replace them with the eigenvalues of B plus C. So now, again, we've swung the pendulum in the wrong direction too much. The definition becomes trivially possible. But this is the space in which we're moving back and forth. You might call this a block respecting approximation. So previously we had a commuting approximation. Now we are only asking for block respecting approximation. And again, approximation is in apostrophes because I'm not really asking for C to be close to B. And this definition reduces to commutativity when the matrix A is diagonalizable. So it is a weaker question, but it reduces to the previous case. Now let me remark something on this condition of the equal spectrum. So if two matrices have the same spectrum, that might not be so easy to check, but the question can be rephrased by saying that there is an invertible matrix, which in general will depend on the matrices A and B, such that when you perform in some sense a basis change, it doesn't have to be a unitary matrix, but if you perform a basis change, then you will go to the other matrix. So you move from one pair to the other by a basis change. And thinking of this as some kind of adapted basis is more useful than asking for an equal spectrum. In particular, it gives us an opportunity to see this geometrically. And so in order to understand this, let's go back to this very simple example that I started with the two Pauli matrices. And the solution that we had for the two Pauli matrices. So I can think of the two Pauli matrices as indicating directions in space, for instance, on the Poincare sphere. So maybe this Pauli Z will point in the Z direction abstractly, and the Pauli X will point in the X direction. And then the matrix A plus B will be somewhere on the diagonal because it has equal coefficients in both the X and the Z direction. And the matrix C, A plus C, is just Pauli matrix, standard Pauli matrix here. And you can see that this is sitting on a circle, right? Because they have the same norm, for example, the same Frobenius norm or the same spectral norm. And you can think of this as a rotation. So this basis change that I talked about is, well, if U is unitary, then it's really a rotation. If U is just an invertible matrix, it might not be quite a rotation, but in this particular case, it is really a rotation, namely a rotation around the y-axis. And so this geometric perspective allows me to think about what I mean when I say it should be an approximation, namely that this is an approximation. So A plus C is an approximation to A plus B if this angle of rotation, roughly speaking, is small. So this is another geometric intuition for another condition we can impose to make our problem harder again, because now it's actually on the too easy side. So I want this to be an approximation. And in order to talk about approximations, I need some scaling. And so the scaling that I will impose from now on is that somehow the norm of A will be much larger than the norm of B. So you can start thinking about B as some sort of perturbation. You will see on the next slide that I will introduce a scaling factor to make this happening. Okay, so this is the key definition of this talk. So if I bored you with my mathematical discourse, then just take this part here as the definition, which will then have the physical implications. So again, I'm just rewriting what I had before. We take two matrices A and B, and we ask whether there is a matrix C such that it preserves the blocks. It respects the blocks of A, the diagonal blocks in the spectral representation. And it is, well, the sum of A plus C is a rotated version of the sum of A plus B, but I've now introduced a scaling factor. You see, I said I want A to be much larger than B, and the way I make this much larger is that I introduce a G, and we will look at the scaling when we make G larger and larger. This way, for any fixed pair matrices A and B, we can actually ensure that this first term is bigger than the second. This is a scaling parameter, as I said. And finally, I want this rotation, or roughly speaking, rotation, to impose a small angle condition. And the easiest way to do this is to say, in norm, this rotation is close to the identity. And how close do I want it to be to the identity? Something in the order of 1 over g, where g is the scaling factor. And if this is possible, this is the axiomatic approach. If this is possible, then the original matrices A and B are called eternally adiabatic. This is the key definition of this talk. So let me just recap 3 aspects. One is it is respecting the spectral blocks. Second, it is isospectral, or a rotation of basis. And thirdly, this rotation of basis should be close to the identity in the scaling parameter g. So as g becomes larger, it should actually go closer and closer to the identity. So a more lengthy definition of this would be that GA plus C is now a block respecting isospectral approximation of GA plus B. But I just call it eternally adiabatic, and I will justify why I call it like this on the next slide. But let me just pause for 1 second here and ask if there are any questions, because this is really the key definition of this talk. Maybe I also want to ask the host how long I should pitch this talk for. Is it do I have until the full hour or 10 minutes to the hour? I'm flexible.
Yeah, Daniel, thank you. If we usually try to keep it to 1 hour, including everything. So if you aim at finishing 10 to 3, we still have 10, 15 minutes for questions.
Excellent. Well, if it's 10 to 3, I actually have more than 5 hours, but I'm sure you meant your time.
Okay, so hour 10 to 3.
Do you have any, does anyone have any questions at this point? Okay, so please interrupt me if you do. So let me introduce the kind of dynamical perspective on this. We had a geometric perspective, but the dynamical is much more interesting. So now let me assume that we have 2 matrices which enjoy this property that there exists such a C. I will not write it down again. And then let's look at the dynamics that A and B generate. So now is really the time where you might start thinking, what do you mean with generating dynamics? They are from some differential equation, and this is the solution of a time-independent differential equation. Maybe A and B are indeed I times some Hamiltonian, or maybe they are even some super operators describing a Lindbladian or something like that. So if you like, think about some physical evolution now, but it could also be the solution of a classical differential equation with constant coefficients. It doesn't really matter at this point. And let's see what happens when I put a spectral projection on one side of this evolution operator. Well, I can just introduce a basis change. This is just an identity here because u minus 1 is identity. And then I can use the fact that this basis change rotates A plus B into A plus C. This is the definition of this basis change, if it is at all possible. But remember, I had the condition also that this U is close to the identity. So I can then actually remove the U without paying too much a price. In fact, the price is just the difference between U and the identity. So it's some error that I make at this point. This is really an approximation, but the error is of order 1 over G. And more importantly, this order is error is independent of T, because it's an error that I do on this U. This U is not a time-dependent transformation, it's a time-independent one. This error is also time-independent, therefore. Now we use the fact that both A and C commute with the spectral projections. A anyway, because they are the spectral projections of A, and C because we've designed C to have this property that it commutes. So we can move the spectral projection to the right side of the evolution. And now we can just go backwards. We reintroduce a rotation. We make another small error. We reintroduce the basis change. And we are left with a similar expression to where we started, but now the projector has gone on the right side. And all we had to pay is a price of g minus 1. So this justifies the name eternally adiabatic, because it means that if A and B generate dynamics, then the leakage between blocks, the leakage between eigenstates, if you like, or more generally between eigenmanifolds, is suppressed. It's actually of order 1 over g. And this error is eternally. So it doesn't matter how long you let your system evolve for, it doesn't accumulate further than 1 over g. So hence we call this eternally adiabatic. And so now you want to see something slightly more quantum. Let me give you one particular quantum example more as a teaser. I will not talk about it much more for the rest, but let's really take some Hamiltonians now. Let's say we have some Hamiltonian H0 and we have some other Hamiltonian V, and let's say that they are eternally adiabatic. So they enjoy this property. And let's consider the Gibbs state, so a thermal state of H0. And now you might ask, what happens to this Gibbs state if it evolves under a perturbed dynamics? So let's consider the time evolution with some parameter epsilon here of the wrong Hamiltonian. So this is not the Hamiltonian with respect to which I define the Gibbs state, because it has the perturbation here. And so in this case, you can think of this epsilon as 1 over g. It doesn't matter if I make this g big in front of here or an epsilon small in front of here. So this is the connection with the previous slide, but it's maybe more intuitive to think of this as a perturbation with a small parameter epsilon. And if this is the setup, then if I look at the Gibbs state, I let it evolve for some time. I compare it with the original Gibbs state. I take the norm distance. Then this, of course, is trivially small for short times, right? Because by perturbation theory, this unitary here will be close to the unitary which only has H0 for some time scale where the time is smaller than 1 over the perturbation strength. But now I take the supremum over all time, and then it is not at all clear what happens in a priori, because even if it's a super tiny perturbation, it could just accumulate over time and become really, really big, right? But the statement is that that doesn't happen. This remains closed for all times. And this is because of this property of being eternally adiabatic. So you have a sort of stability of a state, in particular in this case of the Gibbs state, under perturbed dynamics. And this is actually making the connection with KAM theory. KAM, Kolmogorov-Arnold-Moser were discussing about the stability of, let's say, the solar system with respect to perturbations, maybe comets coming from somewhere or idealizations. And they found that there is a sort of underlying robustness. And likewise, here there is an underlying robustness. You can make this analogy more precise, but I will not do this in this talk. And the proof is very simple, because if you take the Gibbs state, this is just a function of the Hamiltonian. And so in the diagonal basis, it just looks like this. And we have seen on the previous slide that the spectral projections are eternally preserved under perturbed dynamics. So this immediately leads to this equation here. Okay, so this is why I think eternal adiabaticity is an interesting concept. But what I haven't answered yet is under which conditions are two matrices actually eternal adiabatic. I have defined what I want them to be. I have defined the existence of such a rotation and so on. But I haven't asked or answered under which conditions is this actually possible. And so we have a theorem about this, which is characterizes which A and B have this property. And roughly speaking, if the evolution operator of A plus B as a function of time can be upper bounded then A and B are eternally adiabatic. Okay, so this bound here, of course, you could say, okay, exponential of some matrix is always finite, in finite dimensions at least. I'm talking about matrices. But this M should not depend on time. So this theorem I will not explain, but if you want to see the proof, you can find it in this longer paper here. But it immediately implies that any quantum dynamics, no matter whether closed or open, in finite dimensions is always going to be eternally adiabatic. And why is this? Well, if this is Hamiltonians, then this is a unitary, and you can just bound, sorry, there should be norms here. You can just bound the norm by 1. And if these are, GKS generators, you can bound it as well. And then it depends a little bit on which norm you choose. But if you choose, for example, the norm induced by the trace norm, then it's also 1 because they're trace norm contractions. So clearly this is a nice property and it holds for quantum mechanics. So some remarks. So although I will not prove this theorem to you, what is the intuition? So the intuition is that if this evolution here is bounded, then as G becomes stronger, it cannot explode, right? And so if it cannot explode, but G becomes stronger, then one of two things has to happen. Either this term has to become fast oscillating, if it's, for example, a Hamiltonian term, or it has to become a strong decay. And in either case, fast oscillations or strong decay, you can set up some sort of adiabatic evolution. You can use the adiabatic theorem by Kato, essentially. And then what we did is we iterated Kato's theorem to get better and better approximations. And this iteration is similar to what is done in classical mechanics as KAM iteration. And we compute non-perturbative bounds on how close this U-1 can be. And the performance depends, well, it depends, of course, on the strength of B, which is roughly speaking the perturbation. It also depends on the number of distinct eigenvalues of E, on the amount of diagonalizability of this thing, and on the spectral gap of A, or maybe on the spectral gap of G times A, which becomes wider and wider as G becomes bigger. And so we give also explicit constructions of this U and C. It's not just an existence proof. And we give these constructions perturbatively and non-perturbatively. So again, I'm skipping a lot of detail here in the interest of time, but also in the interest of coming to open quantum systems. So I will actually skip the next slide and just go immediately to open quantum systems, because I think this is the more interesting case for you guys. So what I've argued before is that this eternal adiabaticity is a nice and strong feature because it allows us to bound adiabatic leakage. And in order to bound that, we just need the existence of such a transformation, but we don't need to know this C explicitly. So all of the story until now is actually, I don't need to specify C. But nonetheless, sometimes we might like to think of C as some sort of effective generator. So some of you might be familiar with this in the context of, let's say, adiabatic elimination. That's the simplest case. If you have lambda systems, you can think of an adiabatic Hamiltonian, an adiabatically eliminated Hamiltonian that directly couples the bottom states of the lambda system. You would like to think of this as an effective physical generator. And so there's a whole bunch of papers on effective Hamiltonian theory and more generally effective GKS generator theory. In those papers, a lot of the difficulty arises from the fact that this rotation is not unique, because you can always change the rotation a little bit, at least inside the degenerate eigenspaces. You can change it by another rotation, which is of order 1 over gamma, and the result will still be true. So this is a kind of gauge freedom that you have, which is much discussed. And I think there's about 50 different perturbation theories that people have set up just for the unitary case. Now, when A and B are Hermitian, we can actually choose U to be unitary. So I would argue that that's the best possible gauge because it's the most physical one. And in this case, C is automatically Hermitian. And the keyword, if you want to look this up, is the Clouseau perturbation theory from the 50s and the Schrieffer-Wolff transformation from the mid-60s, I think. So in the rest of this talk, I would like to ask the same question for GKLS generators. So when A and B, the original matrices, are GKLS, can C be GKLS? Well, in order to understand this deeply, we would have to understand what kind of basis change preserves the GKLS structure. So for Hermitian generators, it's easy, right? Because it's exactly the unitaries that preserve Hermitianity. But in GKLS, it's much harder because GKLS are super operators. So they live in a super big space, the Hilbert-Schmidt space. And this space is big. So if you choose a basis change in Hilbert-Schmidt space, hell breaks loose, right? Because you're actually, most of these are not reflected by unitaries or basis change on the Hilbert space. They cannot be mapped down. They cannot be brought down to Hilbert space. You might be doing crazy and completely unphysical things. Anyway, we wanted to have a go. So we want to ask the question, can C always be GKLS? That is, it means, okay, I can use this. I can write this down in the structure that is very familiar with you in terms of jump operators. But the way we answer this question is, can it be trace preserving, Hermitianity preserving, and conditionally completely positive? So for channels, you might be familiar with complete positivity, and maybe some of you have seen this formulation, but if not, then this is actually quite a nice way of thinking about the validity of a generator. So even if you're not interested in the example that I'm about to present, you might like the methodology. The first person I know, as far as I know, who asked this was Kessler in 2012. And he only went up to third order, and he found that with a little bit of tweaking of the gauge, you could make things physical. So we were curious, can you make it always physical? And then unfortunately, the truth is we cannot. And this is the annoying counterexample because we didn't like it. We liked it. We would have loved it to be physical, but it turned out not to be true. The counterexample that I want to spend the rest of the talk on is in 3 dimensions. It seemed that 2 dimensions was too simple. And so the GKLS generator that we looked at is of relatively simple form in this 3-dimensional space because it only has one jump operator, L0. The Hamiltonian we have already chosen diagonal. And the jump operator is a simple one because it's a Hermitian jump operator. It's essentially a bit like sigma x. So this is a bit like a dephasing, but it's now in a 3-dimensional space. And that's it. That's going to give us a counterexample. So interestingly, this counterexample is actually diagonalizable. But nonetheless, it is a counterexample. So in order to explain this a little bit more deeply, I would like to go through some of the steps we did. Maybe not all of them, but some. So the first thing we did is we vectorized this. So actually, I haven't said which is A and B because, of course, I need 2 matrices A and B. So the strong part is the one with the G in front. So this is my A here. And I can vectorize my density matrices and vectorize or matricize the superoperators in this way. So those of you who have solved master equations numerically will be very familiar with this way of vectorizing things. And I get a matrix here because the original Hamiltonian was already diagonal. This matrix is easy to understand. It just has the spectral differences here times I on the diagonal. So for example, 1 minus 0 divided by 3 gives me I over 3. And I have the minus I over 3 here as well. I have a 1 minus a 3 minus 0 divided by 3 gives me an I, and so on. So this is just the Hamiltonian component. And then the for the jump operator, I can do the same thing. The formula for the jump operator is a bit more complicated, but you can probably just about make out some structure here. For example, this 1 1 here is exactly this jump operator and comes from the term L tensor L. And then these L dagger L, because this squares to something that is diagonal, all sit on the diagonal. So it's pretty much already diagonal, except for these few ones here. So it's going to be easy to diagonalize A plus B. All right, so for those of you who have a good memory of matrices, I want to highlight the three positions of the zero eigenvalues. Here, there, and there. They will be relevant later. So so the spectrum of A we already had. That's just the spectrum, the difference of spectrum of eigenvalues. So the block structure, if I arrange this threefold zero eigenvalue at the top, is that it's actually got 3 degenerate eigenvalues and the rest is all completely non-degenerate. So the idea of this matrix is that we wanted the block structure to be very constraining, because C has to commute with this thing. So if the block structure is very fine, if it's almost non-degenerate, then maybe that brings us a lot of constraints on C, and that turned out to be true. A plus B is this awful matrix here. And I claim that the spectrum is just this. And you can actually pretty much read off the spectrum. For example, all these values in green are already diagonal. They already live on blocks which have zeros elsewhere. And so I've underlined them in green in the spectrum below, here and there. The spectrum of this block matrix here, the outer block, is also easy. This looks a little bit like a projection, and it indeed is 2 times the projection, or -2. So it has eigenvalues 0 and -2. And then this remaining matrix here can be written in terms of Pauli matrices like this. And then you might be familiar with this, that you get some kind of square root when you diagonalize sums of Paulis. So this is again this here. And just for convenience, I'm assuming that G is larger than 1, because then I can actually say that this is an imaginary component of this eigenvalue. All right. So then the next question is there a commuting GA plus C with the same spectrum that is Hermitianity preserving, trace preserving, and completely positive, conditionally completely positive? So it's valid physically. Now notice that this is a little bit weaker than what I've asked before, because I'm not asking for C itself to be all these 3 things. I'm only asking for the total sum of these the 3 things. Clearly, if C is physical, then A plus C is also physical, but you could have a case where A plus C is physical, but C nakedly is not physical. Maybe A compensates something, but I'm asking for something weaker. I'm asking for the sum to be physical, and I'm not even asking for this rotation to be small. This will already be sufficient to give us a contradiction, these conditions here. And so in order to understand this, I have to look at the most general commuting A plus C that has these properties. I claim that the most general commuting A plus C that is Hermitianity preserving and trace preserving is of this form here. This might look complicated, but it's actually easy to see, because first of all, this is of course expressed in the eigenbasis of A, in which A has this block structure. And so the block structure of this matrix here is immediately clear. So commuting is obvious. Then trace preserving, trace preserving is that the identity is a left eigen operator of your generator. And if you vectorize, this looks like this. This is the vectorization of the identity. This has to be a left eigenvector of the matrix. But I've reshuffled the spectrum a little bit. I've put all the zeros in the top left. So this turns out to be the eigenvector. And so this is why this first block here is not completely independent. There are some minus signs here. That's trace preservation. Hermitianity preserving, roughly speaking, is just that all these parameters here, I have 12 parameters, all of them are real. And why is that? Well, one is that Hermitianity preserving operators always have eigenvalues in complex pairs. So this is where this structure comes from. And then this part here is actually corresponds to 0 eigenvalues for which the eigenoperators are Hermitian, and then this corresponds to the Hermitian part of the basis, and there also the matrix representation needs to be real. You might be familiar that, for example, if you choose a Hermitian basis, then these operators have to be real everywhere. Okay, so this is the most general form. And now I need to impose constraints. And so first constraint comes from matching the spectrum. I want the spectrum of this guy to be equal to this set. But I only want to match the spectrum. I can't say, well, this -2 needs to be here, because the spectrum, of course, is just a set. It doesn't really depend on which order you do the spectrum. So matching the spectrum might be hard and non-unique. I want to avoid this. But one thing I can say is that this block here corresponds to these 3 eigenvalues. It has to. And why is this? Well, first of all, because of trace preservation, this block here has to have a 0 eigenvalue. So this corresponds to 1. And then if there are 2 more real eigenvalues that need matching, but if any of these here had no imaginary part, then they would always give me a real degeneracy of 2, which I don't have anymore. I only have a -2 and a 0. So it needs to be in this block. And so I can impose that the trace of this block is equal to the sum of those eigenvalues. I can also impose that the trace of the other block needs to be equal to the sum of the other eigenvalues, where all the imaginary parts decompose. So I get these 2 conditions here. And this means that I can eliminate 2 parameters. So I only have 10 more to go. But in my mind, I also have 3 minutes to go. So I can't find more constraints like this easily. Instead, I will impose conditionally completely positivity on the next slide. But before we do that, I want to note the imaginary parts of the eigenvalues, because these will lead to the contradiction. So the imaginary parts of the eigenvalues of the ansatz here are just R8, R10, R12. And the imaginary parts here are G/3, 2G/3, and the square root here. And for the contradiction, it will suffice to memorize these. So now comes the last part, which is this conditionally complete positivity. So if you're familiar with complete positivity, what you would do to check if a channel is complete positive, you would look at the Choi-Jamilkovsky state, which comes from the matrix representation of the channel by a particular reordering of all the elements of the matrix. This is sometimes called the reshuffle. And I've this mess of blue arrows here shows that every non-zero eigenvalue of this matrix here has a place in this reshuffled matrix, but it looks ugly. So this is always Hermitian. And for channels, this would be a state, but for GKS generators, this isn't a state. It doesn't necessarily have positive spectrum. If you want to look at the conditionally complete positivity, you need to project away the complement of the maximally entangled state. This is the projection onto the 1 minus omega, where omega is the projection on the maximally entangled state. And if you project this away from the Choi-Jamilkovsky isomorphism, then the condition of CCP, which will then translate to a positive Kosakowski matrix, for example, or to a Lindblad structure, or whatever way you like to talk about your generator, the spectrum condition is that this spectrum here has to be non-negative. And so then this comes to a point where in 1 minute I cannot show this anymore. And so I use Mathematica and I compute this matrix and I compute the eigenvalues. And I find that some eigenvalues have this particular form where C is some real number. And because it needs to be positive, this square root needs to be 0. And this gives me a quadratic equation in R1, which I can solve. But because R1 is real, this square root here needs to be non-negative. And then if I solve in Mathematica for that, I get 2 conditions essentially, these 2 conditions, of which I only need this last one here, because this is a condition, R12 is equal R8 to R10, is a condition that relates the imaginary eigenvalues to each other. And that's the end almost. I just need to say tell you why this is the end. So this is the concluding slide in some sense on the proof side. So the imaginary part of the spectrum, on the one hand, because of this condition here, contains 3 numbers, but they are not independent. The third one is a sum of the other 2. And it should match this, right? Now the ordering doesn't matter, but if you look at the first term, they are all rationally dependent. And the second term is rationally independent, at least for almost all values of G. So they cannot be matched. This is a contradiction. And so therefore, C cannot be physical. So while for A and B Hermitian, C can always be Hermitian, when A and B are GKLS, C cannot always be GKLS. It cannot always be trace preserving, Hermitianity preserving, and completely conditionally positive. Just as a side remark, if we sacrifice CCP, at least we can construct a C which is TP and HP. That's the best we can offer to you. Okay, and so now I come to my conclusions. I've defined eternal adiabaticity by 3 properties. One is block respecting, isospectrality, approximation. And it allows us to obtain some sort of stability against perturbations. I gave you only the example of the Gibbs state. I have some more examples on the remaining slides, but I don't have time to present them. And so any finite dimensional time-independent quantum dynamics, noisy or noiseless, is eternally adiabatic. So it's a useful property. And the effective generator that you get from it, the C, can always be trace preserving and Hermitianity preserving, but not necessarily conditionally completely positive. So as an outlook, why not? Right? So, I mean, you could say, okay, the violation of completely conditional positivity is small. And why do I even want approximations to be physical? You know, like the Dyson series is not physical, but it's still very annoying. And this is because these generators have been used in many, many works as low energy approximations, adiabatic elimination, and so forth. And so I have the problem now that I've worked this out for some physicists, and it turned out that the operator I got is not a valid GKLS generator. And so he wonders, how can he write a paper if he's not presenting a valid generator? And in the future, I want to look at time-dependent generalizations and at infinite dimensional cases, which I haven't looked at. And so last but not least, I want to thank you for your patience and attention. And I also want to advertise 2 postdoc positions. Thank you.
Thank you, Daniel. Thank you very much. It was really, it's really a nice talk and a really nice and interesting topic. Let's see if the participants have some questions. I see Ilya is clapping. Let's see if somebody has a question.
Hello.
Yeah, Camille, come.
Yes, yeah, so thank you for this interesting talk. Yeah, I have one first question, which is the following. So, yeah, I know, I mean, I'm a bit familiar with adiabaticity, but maybe more from dynamical perspectives. And so you probably know that this usual rule, which says that so if you have a quantum system, you drive this quantum system, and so usually people say that if the driving is slow enough, then it preserves adiabaticity, meaning that, yeah, for instance, if you start in a thermal state, you will remain in that thermal state for slow driving. And so my question is how how you can relate that to what you, I mean, is that related to, for instance, the fact that you showed that for finite dimension, I mean, system with finite dimension, such systems are always eternally adiabatic?
Yeah, it's a nice question, and I didn't talk about this, but let me just take it as an excuse to show you this slide, which I skipped, where we had the sorry, it's the one after this one, yeah, where we have the explicit bounds, and maybe this bound will help a little bit explaining the connection. So in the standard adiabatic theorem, first of all, the standard adiabatic theorem is often phrased in terms of ground state properties. You're not leaving the ground state as long as your driving is weak comparison with the gap between the ground state and the first excited state. But of course, this holds for any, you can just shift your energy scale, and you can say any band of eigenvalues, if that band is separated from the rest of the spectrum, then if you are driving weakly corresponding to this band, then you will stay in this band, right? That's the kind of adiabatic dynamical version of the adiabatic theorem. And here something very similar comes in, because what matters to determine the quality of our approximations is the minimum gap between eigenvalues. And so this is a gap condition as well. And this quantity we call eta. And then essentially our bound scales with the number of different eigenvalues and 1 over eta. So you can scale eta. Effectively, you can scale eta by making I mean, if you had a G, you could make it bigger by improving G. Here we make this bound better by making epsilon smaller, but that's the same thing. So indeed, as the perturbation becomes weaker and weaker with respect to the gap, the adiabaticity becomes stronger and stronger. So this is exactly the same thing as the adiabatic theorem that you've referred to. However, the adiabatic theorem is about time-dependent driving. So it has a stronger, a much stronger statement in the terms of allowed driving, because what I'm looking at is essentially, you can think of this as a time-independent driving, because I look at a time-independent perturbation. Sorry, now the slide skipped, but my time evolution operator here is just, with a constant driving time. So in that sense, what I'm saying is much weaker than the adiabatic theorem. So I can actually use the adiabatic theorem to get a similar result. But the adiabatic theorem works only on a particular time scale. And so if you let the adiabatic evolution in the standard adiabatic theorem become bigger and bigger, your error becomes bigger and bigger. Whereas in my case, the adiabaticity is eternal, so it will never stop being adiabatic. So that's the key difference. So on the one hand, we are weaker than the standard adiabatic theorem because we need time-independent driving. On the other hand, we are much stronger because our result is eternal and not finite in time.
Okay, thank you. And so, yeah, but I think you mentioned that maybe at the end. So you are also looking, I mean, interested in the future, maybe to look at time-dependent perturbation, right?
Yes, yes. So
okay.
in the time-dependent case, we can't expect to get eternal bounds. But what you would expect is that you can do much longer than the standard adiabatic theorem.
Okay.
And we have,
thank you.
We've kind of half written something about it, but it's incomplete.
And Daniel, can I also ask you a question, which might be completely stupid? Does this eternal adiabatic approach, does it have some obvious implications for adiabatic quantum computing, in the sense that can you now think of applying it to design better processors for adiabatic quantum computing, or come up with better algorithms, better architectures, or something like that?
We have not explored that side of the coin yet. I think it's an interesting suggestion. What we have looked at is quantum simulations. Mm-hmm. And in the context of quantum simulations, you might have the problem that when you simulate a Hamiltonian, that the Hamiltonian in the lab is never going to be exactly the one that you wanted to simulate. There's always going to be perturbations.
Mm-hmm.
And so you might have to take these perturbations into account, and they will accumulate over time. And almost by definition, you need to evolve your system for longer times in order to have a valuable quantum simulation, because if the short time dynamics for local Hamiltonians can usually be efficiently classically simulated. And in this framework, what we have come up with is a characterization of the set of observables which are robust. And so we think that has ramifications in quantum simulations, because if you can map your quantum simulation algorithm to observables which are robust, then those observables and their expectation values will remain unperturbed even in the presence of imperfections. But also this aspect we haven't completely worked out until the end. So it's just a kind of, the last sentence in a paper where you say this might pave the way towards. It's on that level, basically.
Okay, but it could be very interesting to look into that.
There's a flip side to this also, which is the many-body side. So I mean, infinite dimensions might be hard, but high dimensions would already be interesting. So if you impose some particular structure of locality, which observables are good, which are bad, and so on, how does that relate with concepts like integrability and so on? So those are things that we're very much interested in at the moment.
Okay, fantastic. That would be nice to follow up this discussion and these applications to maybe even to computing. Yeah, that would be very cool. Yeah.
That's a good point with adiabaticity. I mean, it seems natural that it might have applications, but I cannot say.
Maybe we can discuss it in another occasion, or separately. Yeah, because I think that I have the gut feeling that it could be very relevant there, but I don't know. We need to think about it. Yeah.
If you look at transmons and superconducting qubits, the whole business there is effective Hamiltonians in low energy, because you have a harmonic oscillator, but you're cutting off a lot of the spectrum, and then you have an effective generator, effective noise, and so on. So there's a lot of things to be done in the transmon setting, but most of it is interesting when you start doing things time dependently. Because when you, for example, if you restrict your system to lowest two energy eigenstates and you start driving it, the system says, why should I stay here? I'm just shooting off, and then you get leakage and so on.
Okay. No, very interesting. I'm sure there will be many applications of this approach. Yeah. So, are there more questions for Daniel, or can we allow him to go to sleep?
Yeah, I have one last more question.
Okay, please, Camille. Let's conclude with your last question.
So yeah, so you I'm sure you're aware about what's called the shortcut to adiabaticity. I was just wondering how your framework can be related or useful for those techniques, or maybe there's nothing in common. I don't know. Yeah.
Good question again. So, I mean, the way I think about shortcuts to adiabaticity is just an error term in Kato's paper, which he proved to be small. And then people decided, actually, I can artificially inject it or subtract it, and then it's actually zero. So the shortcuts to adiabaticity is artificially introducing this term that enforces the system to be adiabatic. I could imagine that in the time-dependent case, this will be more interesting, because that's where they're usually introduced.
Yes.
In this time-independent case, it's probably a little bit too simple to talk about them. But I haven't thought about it deeply, I must admit.
Okay, no problem.
If you have some ideas, I'd be happy to discuss further.
Okay, yeah, for now, no, but yeah, I was just wondering if there might be a relation, yeah.
Okay, but you know, we are all just at Zoom click away, so maybe we can reconnect and keep the discussion going on in the following weeks. Yeah. So Daniel, I think it seems there is no more urgent questions. So thank you so much for a really nice talk that you know, will give us some food for thoughts for the weekend to think about possible uses of this very nice technology. Yeah. So Daniel,
thank you so much, Francesco.
Yeah, no, thank you, and we wish you a good night, and stay safe in Australia, because this Delta variant, we can tell you with our South African experience, it's quite dangerous in the sense that it's very infectious. So yes, don't let your guard down in Australia. Yeah.
All right. Thank you.
Okay.
See you soon.
You. Have a good evening and a good weekend to everyone. Thank you. Thank you very much. Bye.
Thank you.
All right. Bye. Thank you. Bye.
Bye.